Hi class, welcome to the last video in the Calculus 1 series. This is chapter 7.4, integration by substitution. So this is the first method of integration that we will be learning and the only one. Calculus 2 is left for really methods of integration and more applications of integration. So first let's talk about integrals of symmetric functions. If we have an even function and our bounds of integration are over a negative value to its positive value, so over two opposite values, then we can really just take the integral of half of that interval and double it. Okay, so because even functions are symmetric about the y-axis, they have the same value, right? So we can just cut it in half and find the area of half of it and then double that amount. If our function is odd, then what happens if we have over asymmetric bounds from negative a to a, then that integral is just 0 because we'll have a positive portion and an equal sized negative portion that just cancels each other out. Okay, so let's do an example. So let's take some very standard even and odd functions, sine and cosine. Think about the graph of cosine and what it looks like from negative pi over 2 to pi over 2. This would be an example of an odd function, right? So first, let's just prove that it's odd. The definition of odd is that if I change the sign of the input and of the function itself, then I get the same function. So if I plug negative x into my sign, I get negative sine of x, right? So that's part of the definition of an odd function. Okay, so plugging in the negative form into my input makes my function output negative. That's the definition of odd, right? Sine is an odd function, so its integral is going to be 0, right? Here, if we find the integral of cosine from negative pi over 2 to pi over 2, the same bounds, symmetric bounds. Think about what cosine looks like on this. It is positive only, right? And it's symmetric about the y-axis. So we only really have to find half of it. So first let's prove that it's even, right? So for an even function, if I plug in a negative, I get out the exact same thing, right? So if I plug in negative x to my cosine, it's the same as just cosine of x, right? So plugging in a negative input just gets you out your regular outputs. That's the definition of an even function. So our bounds, we can separate this to just half of an interval, right? And then double that value amount, which is a little bit easier calculation-wise because it's always easy to plug 0 into stuff rather than whatever other bounds we have. So here, the derivative of cosine is sine. We plug in pi over 2 and we plug in 0. We know sine is 0 when you plug in 0. When you plug in pi over 2, you get out 1. So that's really nice. You get 2 times 1, which is just 2. Okay, so here's our graph of sine from negative pi over 2 to pi over 2. Okay, so if you think about sine, if we keep the bounds that we're looking at, you see that we have symmetry here, where one half is positive above the x-axis and the other half is negative. So when I find this entire integral, I just cancel out and I end up with 0. If I look at my cosine function here from same boundaries, negative pi over 2 to pi over 2, you can see that it is positive and symmetric. So what I can do is I can just take the integral from 0 to pi over 2 and then double it, right? So I just find this first half and then I double that amount since that's what happens. Okay, so this coincides with the 0 for the sine function and 2 for cosine because just over half of that interval we've got 1 and then we doubled it, so we got the 2. Integration by substitution is similar to the chain rule. So remember that a integral kind of is the way that we undo a derivative. So integration by substitution is undoing, it's the antiderivative form for, or process I should say, for a chain rule type of differentiation. Okay. So the way that we do this is we make a U substitution. So we're going to look and we're just going to try to say what function is inside of another function, and let's make that U. Okay. Now it's not so much just looking at, okay, what's our function inside of a function. It's more so about what function can I take out or take away or substitute to make it look like something easier to integrate, or something that I'm familiar with integrating, right? So we want to always be able to make the appropriate substitution into our integral, right? So the way that we do this is I make a substitution for a function g whose range is in an interval I, and f is continuous on this interval. So my integral here is f of g of x, g prime of x. That's the form that my integral is in. So I let u be g of x. So instead of f of g of x, I have f of u. If you think about the chain rule here, right, we have the function on the inside, take its derivative, and multiply that. Here we differentiate u with respect to x. So this turns into actually a du dx. And we'll have some equality, so our substitution then will look like the derivative of this inside function here times the differential of x. So let's do an example. So just explaining this from the formula won't make a lot of sense, but doing an example will definitely help out a little bit. So notice that we have sine of square root of x divided by square root of x times the differential x, or with respect to x. Here, notice that the square root of x is something that's inside the function, and then we're also being multiplied by another function that has to do with x. So that is how we understand that this is an integration by substitution problem, because I have a function on the inside, and then I wouldn't know that the square root is a derivative of any sort, but I could guess that it was, right? And so a lot of times just looking at your integral, you're not going to go, oh, that's a substitution problem. Most of the time you're going to look and you're just going to try several methods. Lucky for us, this is the only method that we're going to learn in this class. So in a Calculus 2 course, you would see this, and then you would attempt to try several different methods of integration until you found one that works, really. So for right now, this is the only method that we know. Easiest substitution is say, well, if this was sine of x, this would be a lot easier to deal with. So that's probably what I should use for my substitution. I'm going to say square root of x should be u. That way I can rewrite this as sine of u, right? So if I let u equal square root x, then I'm going to have sine of u. Well, what about this square root of x here? Well, I'll have sine of u over u. But actually, I'm going to have some nice things that happen, because once I have my u, I also have to differentiate it to get this du. I also have to get rid of this dx. So it's not enough to just have x disappear by making this substitution. What about this dx? I couldn't have sine of u divided by u from this substitution and then still integrate with respect to x. That would not make any sense. I need to integrate with respect to u. So I got to change this dx to du. And I don't do that just by saying, oh, I'm going to just change these things out. This is a du now because everything's in terms of u. It does not work that way, right? So I take my u function, which is square root of x, and I differentiate it with respect to x. So Leibniz notation means u prime here turns into du over dx, right? So I'm using the Leibniz notation instead of prime. Square root of x, we know the 1/2 multiplies down, and then we reduce by a power, right? So we're differentiating this u. Now what I can do is I can multiply both sides of this by dx, right? And the reason I do that is because I need to have du isolated. And I need to make a substitution when I do that, so that this square root of x dx that's left over, I need to have in terms of u's. So I'm going to take this and I'm going to multiply it times dx. But first, if I rewrite this negative 1/2 power, we get this form here, the 1/2 times 1 over square root of x. I then multiply both sides times dx, and I have du equals 1/2 1 over square root of x dx. Now notice that this square root of x in the denominator and a dx is what I had left over here. So if I plug in u, I get sine of u. What's left over is square root of x in the denominator position and dx. That is what du is equal to, except we have a problem. Du is 1 over square root of x times dx, but it's half of that, right? So I'm running into a problem because this integral here does not have a 1/2 anywhere, so I can't just make a direct substitution. So what I have to do then is I have to double this du, right? So if I multiply du times 2, then 2 du's is 1 over square root of x dx, which is what I need, because remember, I'm going to have a sine of u, and this 1 over root x dx, that's all the stuff that's left over in x. So my du now, 2 of them, is the things that I needed to substitute to get away. So if I plug all of that stuff in, okay, sine of square root of x becomes sine of u, and this 1 over root x dx becomes t du. So my integral here turns into this integral. Notice how much easier it's going to be to integrate this, right? I know what the integral of sine is. The integral of sine is negative cosine. Okay, very, very straightforward. Here, however, this previous form, I would not be able to do it without making a substitution. I couldn't just integrate this. We don't have any methods available to just make this, there's nothing that this simplifies to, there's nothing I can do. So I have to make this substitution in order to get this form, which makes it much easier to integrate, right? 2 sine of u du is 2 times negative cosine of u plus this constant of integration, because this is an indefinite integral. And remember, okay, I started off in x. Right now, my variable is u. So I have to make sure that whatever I use for u, I come back and I substitute my x in, because if I start in x, I need to end in x, right? So right now I'm talking about u's, but I started off in x's. So I got to make sure I substitute back and go back to my original variable. So remember what we used? I said that u was square root of x. Okay, that was the whole value that we used here. U is square root of x. So that's the substitution that we'll make back now that we have our value. So this will be negative 2 cosine square root of x plus c. That will be my final answer. Okay. So this integral turns into this function. Okay, so just to re-highlight the important parts here, the goal is to look at what could make this easier, right? Sine of square root of x is difficult. So the inside of that is what I would want to make as my substitution. I would rather integrate sine of x, right? Or sine of w or sine of u. So that's what I'll make as my substitution. Then I have to remember that u equals square root of x or u equals whatever. I have to differentiate that thing. And then I have to try to get this du stuff to match what's left over in my integral. Okay, so that's really the process that we're going through here. So let's do a couple more examples. Let's find the integral of tangent of x. Okay, so this is not one that we saw from our list of antiderivatives. Did not see tangent anywhere as far as trying to find its antiderivative, right? So, because we've never talked about what can I differentiate to get tangent, right? We don't know what the antiderivative is. So in order to work this out, what we want to do is we want to turn tangent into sines and cosines, right? So we want to turn this into a rational function. So we'll write this as sine of x over cosine of x, integrated with respect to x. And then we got to think, well, what should my substitution be, right? I can have sine be my substitution and say I have u over cosine, but that's kind of weird. It would probably be easier if I used the denominator function so that I just deal with sine as a numerator. So I'm going to let my denominator be my variable. I'm going to let that be u. It should work either way, but one way works easier than the other. So here, I'm going to let cosine be my substitution. And again, I chose the denominator because it would be easier to leave sine in a numerator position, right? When I differentiate cosine, I get negative sine of x, which is nice because that's what I need. But notice that there's no negatives here. So I can't just say, oh, du is negative sine of x dx, because there is no negative. So what I'll do is, just like before, is I'll move the negative sign to the other side. And now you see I have sine of x dx, which is all the stuff I would have left over when I say cosine is u. So I will replace sine of x and dx as negative du. So this integral becomes negative integral of 1 over u, right? U is in the denominator. Sine of x dx is that negative du. So that's why we have a negative. That's why we have the du. And that's why we have u on the bottom. I know what the antiderivative of this is. The antiderivative of 1 over a variable, which is much simpler to look at, right, than trying to integrate this, is just natural log of u, right, plus that constant of integration. Again, we got to make sure we go from u back into x. So this is going to be negative natural log of cosine of x plus my constant of integration. When I have a negative on the outside, remember what the power rule is for logarithms. So I can actually come in and call this cosine of x to the negative 1 power, okay, which is the same as secant. So this is natural log of secant plus the constant of integration. So the integral of tangent is the natural log of secant. Okay. So when we integrate by substitution for definite integrals, so far we've only been doing indefinite integrals, right? There's no bounds on these integrations. When we do a definite integral where we're bounded and we have to evaluate our integral at our bounds, there's actually two methods for that, okay? There is a method where we change the bounds of integration, and there's a method where we do not change the bounds of integration. The preference is really up to you, whichever way you choose to do it. Me, personally, I prefer to not change the bounds of integration when I'm doing a definite integral, but that's just me. Sometimes it's a lot easier just to change the bounds. So we'll actually go through both cases so that you can kind of choose which one is preferable to you. Okay. So the substitution rule for definite integrals: if g prime is continuous on a closed interval from a to b, and f is continuous on the range of this substitution function that we're making, then the integral from a to b of our chain rule form, right, is a being evaluated at that substitution, my upper bound b being evaluated in that substitution function, g of x, and then we have that substitution that we did before, f of u du. So we'll still make the substitution of u, we'll still take its derivative and try to solve for du and make it fit with the integral as best as possible so that we can substitute and get it into this form. But here we got to change the bounds. We don't have to change the bounds, but a lot of people will. So I'll show you how to do it without changing the bounds and how to do it with changing the bounds. Okay. So our first example, let's find the integral from 0 to 1 of the cube root of 1 plus 7x with respect to x. Now obviously, if you're looking at this, the easiest function to make for a substitution is this 1 plus 7x. If this was just x, the cubed root of x, that would be really, really easy to integrate. So since we have a complicated function in this cube root, that's what's keeping us from integrating smoothly. So that's what we'll make for our substitution. We'll just say that u is 1 plus 7x. Now remember, once we make that substitution, I also have to differentiate this. So I will differentiate with respect to x. So this becomes du dx. This just gets differentiated, so it turns into 7. And then I would multiply both sides times dx. So it will look like this. Okay, so normally what I do is I just write du and then I put a dx on the other sides because I'm kind of doing two things at once, and I also differentiate this as well. Okay, so here if you notice, I do have a dx. Okay, this is going to be the cubed root of u, but what I don't have is an extra 7 on the outside. Okay, so then what I need to do is, that tells me that 1 du is 7 of these things, 7 dx's. So I'll divide both sides by 7 because I don't need 1 du to be 7 dx's. I only have 1 dx. So how many du's do I need? I need 1/7 of them, right? So I'm going to solve so I can match up with what's left over. So then this will become 1/7 cubed root of u and a du. Okay, because the dx is equal to 1/7 du's. For my bounds of integration, right, if x is equal to 0, well, I'm now going to be differentiating with respect to u, not with x. So I got to change the bounds of integration. So when x is 0, my u is, well, let's see, I plug in 0 and I get out 1. So when x is 0, u is 1. So this turns into 1 for the lower bounds now. Okay. When x is 1, my u function, the substitution, is going to be 8. Okay. So my bounds of integration change from 0 to 1 to 1 to 8. Right? So this is what my integral looks like when it's in terms of x, 0 to 1, cubed root 1 plus 7x dx. Once I make my substitutions into terms of u, I have a 1/7 in front now. I have the cubed root of u. Dx is now the du. And my bounds of integration are from u equals 1 to u equals 8. Right? So these bounds now are in terms of u, because I'm talking about u's now. Right? So when I'm talking about x's, this is what it looks like. Here, everything is in terms of u. So the 1/7 du comes from that dx. Okay. This u is from this 1 plus 7x. The cube root is still there. This is a 1 instead of 0, right? Because when I plug in 0 to u, okay, 1 plus 0 is 1. When I plug in 1, I get 1 plus 7 times 1, or 8. Right, so this is my integral. This is a lot easier to integrate than this is, because I can't actually integrate this. So this is the power rule, right? Antiderivative for the power rule, because this is really just u to the 1/3 power. Right, so I can rewrite that as a power. And so this integral becomes 1/7 times, so if we add 1 to this, this turns into 4/3, right? 3/3. This turns into 4/3, so we multiply by the reciprocal. So this is 3/4 times 1/7. The power 1/3 goes up to 4/3, and I evaluate at the bounds of 1 and 8 for u, right? So I'm going to plug in u is 8, and I'll plug in u is 1. So I got 3/28. Looks like this, right? 1 to any power is just 1, so that's nice. I can rewrite 8 as 2 cubed so that I can cancel out with this cubic that's here, right? This cube root. So then this really turns into 3/28 times 2 to the 4th minus 3/28. So we could pull this out as a common factor if we want to and just say, oh, it's 3/28 times 2 to the 4th minus 1. 2 to the 4th is 16. 16 minus 1 is 15, so it's really 3 times 15 over 28, so that is 45 over 28. Okay. Right, so just like the same thing here, if I pulled out the common factor, I'd have 16 minus 1, or 15, times a 3, right? So I didn't pull out a factor here, but if I did, you can see how the math might be a little bit nicer. So that's my answer, 45 over 28. So let's do this one more time. But instead, let's not change our bounds. Let's keep our bounds in terms of x. and we'll talk about how we can do it that way. Now, one way might be easier for you, neither way is easier than the other, but maybe you prefer one over the other, right? It's really, so now it comes down to a matter of preference. So this is how you would do it if you change your bounds of integration into terms of u. So let's say that we did it without changing our bounds and kept it in terms of x, right? So here we make the exact same substitution. None of that changes. It's still, u is still 1 plus 7x. I still differentiate with respect to x, right? So I still get a du is 7 dx. Again, remember, this turns into du dx. This turns into just 7. And then I have to get all the x stuff on the other side, so I multiply both sides by dx. And that's why it looks like du equals 7 dx. Okay. You saw that on our first example here. Okay, I didn't do it on this one, but I did do it on the very first one. Here, right? Du dx, and then you multiply both sides times dx. Right, so we do that all the time, so I always just instantly write du equals, and then I take the derivative, and then I just write a dx at the end. So if you're ever confused, how'd you get here? That's what I do. Okay. Just skip a step. Alright, so here, so everything is the same. Du is 7 dx. I gotta solve. There's no 7 present here on the outside of this substitution that I'm making already. So once I have this substitution, there's no 7s anywhere else, so I gotta kind of move it over. That's really my thought process. The only thing that's not accounted for is this dx, so since I have something with that dx, I have to isolate it so that I can just make my substitution for dx. Okay. So without changing my bounds of integration, I still have my 1/7 from here. I still have my cubed root of u, because this cubed root of u du, but here I'm keeping x equals 1 and x equals 0. The reason that I don't change the bounds, personally my preference, is because I don't want to do extra math. Really is what it is. Although it could be harder to make this change later, right? So it's really just boils down to preference. So I still integrate everything like normal, because remember, I don't have to use these bounds until I evaluate my antiderivative. So I'm going to go ahead and just find my antiderivative. I know this is u to the 1/3, right? Pull this out and take its antiderivative. Notice here, again, my bounds are in terms of x, but my variable is in terms of u. So before I can plug in x, I can't just go 1 and 0, because I know from this last one, if I'm in u, I have to use a and 1. So what I can do then is that if I'm going to stick with x and never change my bounds, I got to plug in my value back for u, right? U was 1 plus 7x, so I will plug that in. Okay, 1 plus 7x to the 4/3. Now I can evaluate this at 1, and I can evaluate this at 0. It's literally the exact same work, right? So when I plug in 0 here, it's just like when I had to evaluate the bounds here and plug in 0. And when I plug in 1, it'll be just like when I had to evaluate the new bounds and plug in 8. So it's the same amount of work. It's just, do I want to do it at the beginning or do I want to do it at the end? And I'm lazy, so I do it at the end. So I'm going to plug in 1, so that'll give me the 8. Okay, and I will plug in the 0, which will give me the 1. So I'm still plugging in 1 and 8. Right? That's still the values that are getting plugged in. And then the math is the same. Everything is the same. 2 to the 4th. Then pull this out, and that's 45 over 28. So if you don't want to change the bounds at the beginning, you can wait until the end. Just don't forget to change the bounds. The number one thing I see here is that people forget that they're in u, and they never change the bounds, and then they plug in 1 and 0. And then that's where you get into trouble. So if you're not going to change your bounds at the beginning, then make sure you don't forget to change back into x, right? If you're keeping it in x all the time, well, after you find your antiderivative, make sure you make that substitution back, okay? I think we have one more example. So here, let's go ahead and find the integral of x over square root 1 plus 2 to the x from 0 to 4. So let's go ahead and have you guys try this one. I'm not going to lie, this one is a little bit tricky, but I want you to play around and see if you can get it. So go ahead and pause it now and try your best, and then let's come back and check our work together. Alright, so we're back. So hopefully you attempted this problem. What do you think our choice for u should be? It should be pretty straightforward. Obviously this one in the bottom is kind of a lot compared to everything else that's going on. The most complicated looking thing here is this 1 plus 2x that's under square root sign. So let's go ahead and make that as our substitution. Okay. And if we differentiate both sides and then multiply times dx, we get du equals 2dx. Now the problem here is there is an extra x laying around, okay, and there is no extra 2 laying around. So from first glance, maybe that wasn't our right choice, or from first glance, maybe this isn't the right method to use, right? So in the Calculus 2 class, generally what would happen now is that we would attempt another method to try to differentiate or integrate. But we're not in Calc 2, and this is the only method we have, and I'm not going to throw you a curveball, so we can actually finish this out with substitution. So if this is as far as you got and then you got stuck, that's fine, because that's a good place to get stuck at. The problem is that, yes, I have a dx, but I don't have 2 of them. I also have an x here that is not present in this differential form. Okay, so first things first, let's go ahead and get our dx part to look the same. So we will have this 1/2 du equals dx. So what about this x? Well, we can actually come back to our original substitution and solve it for x and make another substitution. Okay, so if we solve this for x, we will get u minus 1 divided by 2. So again, this is the problem that we have. If I make the substitution for the dx equaling 1/2 du, I get my 1/2 du for the dx. My u into the square root is square root of u, but I have this x here that is not present from the substitutions that I need to make, right? So what I do is I can solve this for x. Okay, x is 1/2 times u minus 1. So now my integral is 1/2. Here I'm keeping the bounds in terms of x, decide not to change them, and I got a 1/2 u minus 1 over root u. So as it stands, it still looks like something I'm not able to integrate, so I want to simplify things first as much as possible. So I'll distribute this 1/2 back to the outside, and then notice that I'll have u over root u, and I'll have 1 over root u. So I can rewrite this as not a polynomial, but in power form. Okay, so I got this u minus 1 over root u. I can simplify those two terms, and this is, so 1 minus 1/2, so that's 1/2, and then this is negative 1/2. So here I can just use the power rule to finish integrating. Okay, so this goes up to 3/2, and this goes up to 1/2, and then obviously we multiply by the reciprocal of those new powers. So I have my 1/4 that was already here. I could have left it out as a multiplier times the whole thing, or I can keep it to each term. It's up to you. So this is 3/2. The reciprocal is 2/3. This was 1/2. The reciprocal is 2. I could simplify those if I want to. Notice here I kept my bounds in terms of x. So I need to take my u's and I need to resimplify. So 1/4 over 2/3. The 2's cancel out and I get 1/6. This goes to 1/2. I make my substitution for my u's back in because I never changed my bounds. So now that I'm back in terms of x, I don't have to write x equals anymore, right? Because here, if I don't write x equals, it's very easy to get confused and say, oh, I just got to plug 4 and 0 into here. But I can't because x is 4 and 0. My variable here now is that u sub that I used. So I come back into my x's, which means I don't have to write this as x anymore. I can still write x equals 4 and x equals 0, but it's not necessary because it's implied that I'm in the terms of the right variable at this time. So I just plug in 4 everywhere. So this is going to turn into 9, and then this will turn into a 9, and I will subtract from that, plugging in 0, which will turn this into a 1, and this into a 1. Okay. So I have my 1/6, 9 to the 3/2, minus 1/2, 9 to the 1/2. Subtract from that what happens when I plug in 0, which makes this just 1 times 1/6 and 1 times 1/2, and I'm subtracting those. I'm subtracting this amount from this amount, so that's why I got a set of parentheses here. 9 can be written as 3/2, and so those values will cancel. This 2 and this 2 here will cancel. This 2 and this root cancels as well. So this turns into 1/6 times 3 cubed, or 27. This turns into just a 3. Here I'm making my common denominator. And when I simplify and distribute this negative, I get 1/3. Okay. So here, 27 over 6, that simplifies as well. Okay, so I have 9/2 minus 3/2 plus 1/3. Combine all of my fractions together, right? So this turns into 6/2 or 3 1/3, okay, which is 20 over 6, which reduces to 10/3, right? So that is 3 1/3. That is it for our Calculus 1 sequence. So I will see you guys whenever it is that I start to do a Calculus 2 sequence. I hope you guys enjoyed it.